I rank the 5 voltage steps inside an AI data center by how brutal each drop is. Number 1 isn't the grid. One network drops 13,800 volts down to the volt a GPU die needs. Here's the trap. A modern AI GPU die pulls over 1,000 watts at under 1 volt. That's hundreds, nearly 1,000 amps, crammed into a chip the size of a fingernail. Feed it 13,800 volts and the die vaporizes. Feed 13.8 kilovolts worth of amps at 1 volt and the wires melt. The network exists to reconcile all three: voltage, current, and heat. And immersion cooling is the only reason this survives. Start at the fence. The utility feeds the campus at medium voltage, and the first big transformer at the data center's own substation steps that down to 13,800 volts for distribution across the building. Why 13.8 kilovolts? Here's the rule the whole video runs on. Power equals voltage times current. Hold the power fixed, and if you push the voltage up, the current drops in step. Low current is the goal, because the heat wasted in a wire climbs with the square of the current running through it. Double the current, quadruple the loss. So the network moves power around the building at high voltage and low current, which lets the copper stay reasonable and the losses stay small. Think of it like a highway. You keep traffic moving fast on the wide road and only slow it down at the exit right by the destination. The same logic holds here. You distribute at kilovolts across long runs, and you only step the voltage down when you're close to the load that actually needs the low voltage. Step it down too early, and every foot of cable after that fights huge current and bleeds heat. But that raises a question. How far down does the next step go and where? Now the first real step down. That 13.8 kilovolt spine feeds smaller unit substations scattered near the rack rows, and each one steps the voltage down to 415 volts, sometimes 480, delivered as three-phase power. From there, power distribution units and overhead busways carry that 415 volts out to the rows of racks. This is the level a facility's electrician would recognize. But watch what happens to the current. The power hasn't changed, and we just cut the voltage from 13,800 down to 415. That's a drop of more than 30 times. So the current has to jump by that same factor to keep the power constant. The wires feel it. Where the 13.8 kilovolt spine was a slim run, the 415 volt busway feeding a hot row of AI racks is a fat bar of copper or aluminum, sized to carry hundreds of amps without overheating. This is the pattern you'll now see repeat at every stage. Voltage down, current up, conductors thicker. Each time we get closer to the die, the wires get heavier for the same watts, which sets up the strangest step of all, because inside the rack the power isn't going to stay as a C. Inside the rack the current gets converted. A power supply, really a rectifier, takes that 415 volt alternating current and turns it into steady direct current on a shared rail. In the AI racks driving this build-out, that rail is very often 48 volts direct current, running down a solid copper busbar built into the back of the rack. Why 48 and not the 12 volts older servers used, or the 1 volt the chip wants? 2 reasons. First, current again. At 48 volts you push about 16 times less current than you would at 3 volts for the same power. And since wasted heat scales with current squared, that slashes the loss burned in the rack's own wiring. Second, safety. Anything under about 60 volts is treated as low enough that a technician brushing the bar isn't in serious danger. So 48 stays on the right side of that line. So the 48 volt busbar becomes the shared spine of the rack. It runs the full height of the shelf, and every server tray, every board simply taps into it. Power arrives at the tray still at 48 volts. But the GPU can't touch 48 volts. It needs ones. And that last drop is the hardest one in the whole chain. This is the last mile, and it happens in millimeters. Sitting on the board right next to the die is a cluster of tiny converters. Each one is a voltage regulator module, and together they drop that 48 volt rail down to the roughly 0.7 to 1 volt the GPU core actually runs on. They sit millimeters from the die on purpose, because at these currents distance is loss. Here's the clever part. One converter can't handle the whole flood of current, so the job is split across many working in parallel, often 10, 20, or more of these phases. Each phase carries a slice of the near 1,000 amp load, and together they act like a bucket brigade handing current to the die. Splitting the work does something else too. A GPU's appetite swings wildly, going from near idle to full throttle in microseconds, and a multi-phase design can react fast enough to hold the voltage steady through those swings. But every one of these converters is imperfect, and whatever power they waste turns into heat deposited millimeters from a die that is already the hottest thing on the board. That's why where these regulators sit and how they're cooled matters as much as the chip itself. Which brings us to the heat. Now the other half of the story. Every one of those conversions, 13.8 kilovolts to 415 to 48 to 1, is imperfect. Each one skims off a little power as waste heat along the way. Stack that on top of a die already burning over 1,000 watts, and you've concentrated a staggering amount of heat into a volume smaller than a coffee mug. Air simply can't drag heat out fast enough at that density. The silicon would cook. This is where immersion cooling comes in. Instead of blowing air across the boards, engineers drop the whole board into a bath of special non-conductive fluid, a liquid that touches every live component without shorting anything out. That fluid pulls heat off the hardware far faster than air ever could, letting the current density stay brutally high without the chip overheating. And the heat doesn't stop there. Pumps push the now warm fluid through a heat exchanger, which hands the heat off to a separate water loop, and that loop carries it outside and dumps it to the sky. So trace it. Current flows in and steps down, stage by stage, toward the die. Heat flows out stage by stage away from the die. Two rivers running opposite directions, meeting at one chip. So here's the whole staircase in one breath. Grid power arrives and drops to 13,800 volts for the building. A unit substation cuts that to 415 volts for the rack rows. A rectifier turns it into a 48-volt direct current busbar down the rack. And a ring of multi-phase regulators makes the final plunge to about 1 volt, right at the die. At every single step, voltage trades away for current deliberately to keep the wasted heat in check. And running against that flow, heat leaves the die through the immersion fluid, out to the exchanger, out to the sky. Current and heat out meeting at the chips. That's the answer to the puzzle we opened with. The 13,800 to 1 drop was never one giant transformer. It's a staircase, and every step is exactly where it is for a hard physics reason. Push the voltage down too early and the wires melt. Too late and the chip fries. Each stair is the compromise that keeps both from happening. Every AI data center on Earth runs some version of this same voltage staircase, grid to die, no matter whose chips are inside. Next time, we follow the heat the rest of the way out, into the cooling towers and chillers that decide how many of these machines a site can even run. Subscribe and we'll open that box next.